Hey guys, so today I'm going to review and talk about just the really important parts from lesson 5.1. This is talking about endothermic and exothermic reactions, so like change in delta H or the change in heat energy in reactions. Our delta G are Gibbs free energy. Equilibrium, what that means, and equilibrium constants, equilibrium expressions, and then Le Chatelier's principle and how that has to do with equilibrium. I'm not going over every single thing in the lesson. I'm just hitting them, what I feel like are the most important points for you to focus on for this week. So let's get into it. First off, sorry. Okay, so endothermic and exothermic reactions. We're looking at delta H. And H in this case, it's not temperature, it's our heat energy. Okay? Not the same thing as temperature. Okay, it's like the energy that is either absorbed in a reaction or the energy that is released. Okay? So say I had this reaction, A plus B equals C. Okay? Let's say this reaction happens and when it happens, it blows up. So this huge explosion happens when it goes off. And then it forms this gas, C, and this gas floats in the air, okay? This reaction released a ton of heat. It made an explosion, and it released a lot of energy. That means it's going to be an exothermic reaction. Exothermic means heat is exiting the reaction. So we could even look at it as if heat is a product, okay? Energy in the form of heat is leaving the reaction. And if you think about it, if there was a lot of energy over here, like let's say there was this huge buildup of just energy, and it's like, if there's a lot of energy in one spot, it's not as stable. So when the energy is released, usually that's going to be relieving. I've talked about this before, like if you have a pimple and it's like swollen, it's red, and it's like has all this energy built up, and then when you pop it, it's like it releases that, and the skin is probably much happier that it's not swollen anymore like that. Okay, so it's like releasing energy in the form of heat. So with an exothermic reaction, you can kind of look at it as if heat is one of the products. Okay, it's giving off heat. Okay, and since it's losing heat energy, our delta H is going to be negative. So we're going to have a negative delta H. A delta H just means, just like with delta T was change in temperature, delta H is change in heat energy. Okay, so there's a negative change in heat energy, meaning we lost heat energy. And in this case, in chemistry, that's a lot more stable. Okay? So now with endothermic reactions, you can probably guess endothermic just means you are putting in heat, like the reaction requires heat. Okay, so it gains heat energy. And just like exothermic was like exit, right? Heat is exiting. This is endo, which means it's like going into, and you can even think of like en, like in, right? Heat energy is going into the reaction. Okay, so let's just flip this around, because in this reaction, like all reactions, usually instead of like a single arrow right here, actually in chemistry, we'll go over this with equilibrium more, but we write like a double arrow here, because with most reactions, they go both ways. Most reactions are reversible, and they can go one way and then they go the other way as well. So this exact same reaction, we could draw it like C makes A and B. If you like go the other way, C would form A and B. You could even look at it as if it was like A and B form A plus B, right? Just doing C just because, yeah. So this is the reverse reaction that we just did up here. Since heat is over here, you're inputting heat into the reaction, and it's causing it to go forward, right? Something happened. C. Sorry. There we go. So in this case, energy is being input in the reaction. It causes technically causes you to gain energy. So delta H is going to be positive, right? You're inputting heat into the reaction, and then you're creating these. So in this case, the products here are going to have more heat energy than the reactants. So we're like energy small. This is lower energy, and this is higher energy over here. Okay. If I drew this like a graph, this can help you kind of visualize this. An exothermic reaction, let's say this is like energy, or this is like, I'll just say H, our heat energy, and then this is time. Okay, so when the reaction starts right here, it's starting at a higher energy, and then what happens is the energy goes up, and then the reaction goes, and then right here it drops in energy and it releases this energy. Okay, for an endothermic reaction, kind of looks the opposite. We start down here at lower energy, we gain a lot of energy, and then it kind of settles down and right here, and this is like the final point in our reaction. This is the final point. So you can see how this released energy, this is endothermic, it released energy right here and came to a lower point. And this is just the reverse of the graph. We had to put in a lot of energy in order to make it go through. There was still some energy required because any reaction requires energy, and I'll get to that in just a sec. But this one required a lot more energy because it's endothermic. You needed to put in a lot more heat in order to get it out. Okay, so this gets us into another term called activation energy. Okay, and just like I was saying, every reaction needs some sort of energy to make it start. It has to come from somewhere, right? So, sorry. That's why a lot of reactions, like if you watch the videos on Canvas, it was like a balloon. It needed like a flame, a little bit of energy to start the reaction, and then it released this huge flame, right? That is an exothermic reaction because we're doing a little bit of energy right here, just like we saw up here, putting in the flame, and then boom, it all reacts, and then this large flame is created, right? So activation energy is the energy required to initiate the reaction, or the minimum amount of energy. So the minimum amount of energy to initiate the reaction. Okay, so in these two up here, what's the activation energy? We can see right here, this is where like the reaction actually starts and then it releases. So our activation energy would be this right here. Okay, and our activation energy for this endothermic reaction would be that. Okay, so you can see how an endothermic reaction has a much higher activation energy. And as you can see here, it's also just the reverse reaction, right? If we just reverse it, there, go this way. It's the reverse reaction. It requires a lot more energy to start it, okay? So, hopefully that makes sense of what that is. Pretty straightforward. Here's an example of like an exothermic reaction. So if I take a molecule like this, CaCl2, this is a salt, and if I put it into water, okay, here's my water, right? Usually, like we talked about with molecules like this, it dissociates into ions. So we're going to have Ca2 plus and then 2 Cl minus ions. These are going to dissociate and dissolve in the water, and they're going to start interacting with these water molecules. So if we zoom in here, this is inside of our water. Here's our water molecule. I'll draw two of them. Okay, and then here is our ion. Okay, and if you remember if you remember our intermolecular forces, one of them is called ion dipole. Right? Ion dipole interactions. And that's exactly what's going to happen here. We have an ion, and then we have a water molecule, which, as you know, has a dipole. There's a positive side there, and then a negative side here. And this this calcium ion is going to form these ion dipole interactions with the water molecules, and it's going to be very, very favorable because, as you know, these are the strongest type of intermolecular forces. Ion dipole interactions are the strongest type. So it's super stable, and chemistry loves stability. That's what everyone likes, and that's what the world likes. So this is going to be exothermic because, like I said, exothermic usually makes it more stable. It releases energy and it makes something more stable. So when we put these molecules, a Cl2, into water, it dissociates into ions, and then it releases energy because it's having these interactions are happening with water. The same thing's going to happen down here with the chlorine ions, but it's just going to be like interacting with the positive side of the water, like, because of course it's negatively charged, but it's the same thing. An ion is interacting with the dipole and it's going to release energy. So that's like an example that kind of ties things together, just showing you what exothermic can look like in a reaction, but specifically in like ions being dissociated into water. Okay, so next let's talk about catalysts. So this is actually jumping ahead to lesson 5.2, but this is also super relevant here. What a catalyst is something that speeds up a chemical reaction. Okay? Makes it go faster. So if I'm like, trying to think of an example. I don't have an example. Let me look one up for you. Okay, I don't have an example. But what I think of like immediately is if like you're trying to cook, here's my pan. Let's say I'm trying to cook some potatoes. Okay, if you know anything about cooking potatoes in a pan, if you just put the potato in like this, like let's say I like chopped them into like French fries, right? I just put them in here. It's gonna take a long time for them to cook. But if I put oil in the pan, right? Put some olive oil in the pan. Here's now there's olive oil, green. And then I put the potatoes in. It's going to cook them a lot faster because olive oil gets really, really hot, causes it to cook faster. Now, this isn't an exact example of a catalyst, but it's kind of what it does. Something that the reaction can go on its own and it requires a lot of energy, but a catalyst will just make it go faster and make it go like, do a lot more and make it happen a lot easier. This happens all the time in our bodies. And how this happens is, let's draw one of these graphs we had up here. Right? I was just showing you a reaction graph. This is where it's starting. And like I said, this is the activation energy. Okay, so this is how much energy is required in order for the reaction to go and like go down the slope and happen, right? What a catalyst does is it lowers this activation energy. So once you add the catalyst, the graph is actually going to look more like this, right? It starts from the same spot, but you only have to get over this little hump before you go down. It's a lot easier and you don't need that much energy to actually do it. So it'll happen way quicker and way easier. Okay. So, how does it do it? It lowers the activation energy. Okay. And this would be the same thing with the reverse reaction for the endothermic reaction. It would just look be the other way around. It would look like this, right? Instead of needing this much energy to react it just needs like that much. So still needs some because it's endothermic, but not as much because we lowered it with the catalyst. Okay. So another really important thing about catalyst is that it is not consumed. And basically what this means is that like the catalyst comes in and it comes out of the reaction. So if I have this reaction I showed you up here, A plus B equals AB. I'm going to do AB because I'm going to use C for catalyst. And I put in catalyst, C, it's going to come out just as C. It's not going to change. It's not going to do anything. It literally is just, it's like a vehicle. It comes in, speeds it up, and then it comes right out as C again. So it's not consumed, it's not used up. It comes out exactly how it started. So that's a really important thing to remember about catalysts. Okay? Cool, so that's the main thing with like endothermic, exothermic reactions, all of that. After this, we get kind of into Gibbs free energy. And this isn't something we go super in depth into, but the really important thing, this can help us understand equilibrium. So I'm just going to put equilibrium up here because that's kind of what this whole topic is. But delta G, or our change in Gibbs free energy, can help us understand. So just to differentiate, delta H, this is our change in heat energy, right? And delta G is change in, it's called Gibbs free energy, but I'm just going to name it total energy for now. Okay, just because we don't need to get into equations and how it works, but I just want you to understand this is kind of the total energy of the reaction, and this helps us determine which direction the reaction will go. It's not just about endothermic and exothermic. Usually exothermic reactions are more favored and it's going to go in that direction, but there's a few other factors that actually play into it, such as entropy, if you know what that is, and the temperature that the reaction happens at. You don't need to know entropy, but I know some of you have discussed it in like I've seen in the group studies, you've mentioned it. This is where it comes into play. If a reaction is entropy favored, enthalpy flavored with, I guess this is just another word for enthalpy, heat energy. It's like the total amount of heat energy, enthalpy. I should have gave that term before. I'll write it in bigger numbers so you can remember it. Enthalpy. Okay, so this is delta H. But yeah, so our delta G, or Gibbs free energy, this is our total energy of the reaction. And basically, it's like our energy budget. It basically is saying like, let me draw this here. We want our energy in the reaction to come out to be 0. We want G to equal 0. And you've probably seen like if G is less than 1 or G is positive, G is negative or G is positive, things like that. This is kind of what it's saying. It wants to be at 0. This is where it would be the most ideal. Okay? If it is positive, so if delta G is positive, and then if delta G is negative. And I drew this thing up here because this, imagine like this is like a hill, okay? Or like a skate ramp. And this is where we want to be. This is where our ball wants to be, is right down here in the middle, because it's not going to go anywhere. It's stable. It's achieved like the sense of equilibrium where it's not going to go down this way. It's not going to go down this way. It's also not going to go up. It's just going to stay right here where G equals 0. There's no more energy, right? If you know physics, it's like potential energy. It's like this is now where all the energy is kind of gone. There's no more potential energy. There's no kinetic energy. It's just sitting right there at the bottom, okay? If delta G is negative and it's over here, it's going to want to go forward. It's going to want to go in this direction, okay? So it's going to want to come closer here till it reaches 0. If delta G is positive, it's going to want to go in the reverse direction, this way. So it's going to want to come back to here and come to 0. Okay? So this isn't a concept you really need to understand in depth. I'm just trying to help you understand that, like, this tells us which direction our reaction wants to go. If it's negative, it's going to go forward. If it's positive, it's going to go reverse. Okay? And then once it's here, it's going to reach equilibrium, and this is where the chemical reaction doesn't shift anymore. Okay? And I'll come back to this and kind of reinforce it once I talk about equilibrium. But what equilibrium is, it's called equilibrium. Like many of you might think it's like would be called completion. because it's like, oh, but isn't that when the reaction is finished, the chemical reaction is done? That's not actually what happens with chemical reactions. It reaches a state of equilibrium. Okay? And basically it's called that because when a chemical reaction goes, let's say we have this A plus B. Remember I drew this reverse arrow, this arrow right here, C plus D, okay? The reaction can go forward. It can go from A plus B and make these as products, or it can go the other way, right? And that's why I drew these two arrows. It goes both ways. And what equilibrium is when the forward direction and the reverse direction are happening at the same speed. They're happening at the same time, so it's equal. It's where the forward and the reverse reactions are equal. So it's not necessarily moving anymore. The forward reactions and the reverse reactions are happening at the same rate. Trying to make this so it makes sense, because it can be kind of confusing to explain, especially when we haven't gone over like kinetics, and we're not really going to go over that. But imagine this is like if we have a ton of A and B, we have a ton of this, and then delta G is going to be negative, right? It's going to start going this way, and it's going to start making C and D. Sorry. It's going to start making products, okay? Once it's made enough products, these products, once they're made, they're going to start actually they're going to do the reverse reaction, because it just happens on its own naturally. But once they're happening at the same rate, it's equal, and they're both happening at the same time, and they're the same amount, okay? So let me just try to reinforce this and help you understand. Think about like a soda bottle, okay? Do my best to draw this here. They look more like this. Okay. Oh gosh, sorry. There we go. Not too bad.